Hello, this is the fourth lecture this week. Last three lectures we discussed elliptic integrals, the theory, and in the third lecture we also some implementation in MATLAB. Today we go a little further and then see what we can do with the large displacement analysis of a cantilever beam. So, we look at a particular idea today which is called kinematic approximation of the locus of the tip of the cantilever and what we can make out of that. So, let us look at this particular concept of kinematically approximating the locus of the loaded tip of a cantilever beam. So, let us recall our elliptic integral solutions, the essence or the gist here. We considered three cases where there is purely transverse force, like in this over here, that is the first case, and then there is an inclined one, second case, there is a force and a moment, and you can also consider a case where there is inclined force and moment and so forth. For each of these three cases that we discussed, there were corresponding equations that we needed to solve. That is, in this particular case, the first one, we need to find the value of p. In all these cases, we need to find p. We have to solve this elliptic integral equation to find p. Once we have p, we know everything else, right. Similarly, in the case of inclined load, the alpha is there. For given alpha and force and E and I, again we have to find what p is for given length L prime here. If this is L, this is now L prime length, and this again L, there is moment and a force. You can see where the moment is, and of course, force is where it is. So, in each of these cases, we have to solve the respective equation to find p. Once you have p, everything is known about the elastica that we have talked about in the last three lectures. Okay. Now, let us see what we can do with this for compliant mechanisms. Let us look at this loaded tip and its coordinates, so that we can trace that, we call it the locus of the loaded tip as the force is increased from 0 to some value, and how does the cantilever deform is what we have seen. Now, let us pay attention to the locus of the loaded tip. For that, we start with this non-dimensional number eta, and then this phi b which has p in it, that p we have to find as we just said. Once we find that p and this phi b is known to us, that is the change of variable corresponding to theta equal to 0, where the cantilever beam is fixed. So, when the beam is like this point is what we call b, that is why I am calling it phi b rather than calling it phi 0. Phi 0 is when this bends like this, when we extend it over there, this is where phi is equal to 0, here phi is equal to pi by 2, if you recall. That is what we have. Then we can get w and x by fixing the coordinate system over here. This is x and that is w. The tip here, what kind of a locus it would have is what is given by these two equations. Once we solve for p, as you vary the angle phi, that goes from phi equal to 0 all the way. In fact, this angle that we have, this is should not be pi by 2, it should be also phi b we have, and this should be also phi for any angle. Pi by 2 is at the end, so this should be changed to phi. That is what we have, we can get at any point, right. Now, let us plot it. That is what I have done here using elliptic integral solution. This is plotted, the red curve. It has an interesting property. So, as I change this force from f equal to 0, larger number, the cantilever beam which deforms like this, right, that we have seen. So, the tip is what we are plotting here, coordinates of the tip, and it has an interesting property that it subtends an angle of pi by 8 no matter what this length is, what material it is, that is E value whatever it is, and whatever I is, that is cross sections property, second moment of area. Irrespective of what those are, if you were to apply large enough force, the locus of this loaded tip will trace a curve, and that curve eventually will make with the horizontal, that is parallel to the beam, an angle of pi by 8. This is something that we can derive from those XL, X by L and W by L equations. It is not straightforward, but you can get there. So, there is something very fundamental about the way the kinematics works here. I say it kinematics because kinematics is about geometry in motion. Here a cantilever beam is in motion because of the force that is applied. It has some inherent invariant pi by 8. So, there are many such insights that one can gain in this large displacement analysis of beams, but what do we do with that is our question now. Let us say we take this problem. We have a beam here which is fixed at this point and it is pinned over here, and I have two rigid bodies. So, we can call this a partially compliant mechanism. If I apply some force over here, it is bound to move. How does it move? How do we solve this problem? That is, if we are given this beam, we know its Young's modulus, second moment of area, and of course, the length, we know this. Let us say when I apply a force here, how does it move? It is like a RR rigid body chain with some spring added. If I look at the elastic segment or beam as a spring, then it is spring loaded, and it will, when I apply a force, it is going to move by certain angle of rotation here, as well angle of rotation here and then here. How does it move? If I want to ask that question, can we do? The answer is yes, we can solve this problem because we know how to deal with the large displacements of beams. Now, it is fixed and pinned. When this moves, let us say I apply this force here or apply a torque over here, this is going to move. This beam will have, because a pin joint, will have force in some direction as this pulls. When it pulls, it is going to have a component along that and a component along this. There is a transverse force, axial force. We know how to deal with that based on the elliptic integral solution. So, we can actually solve this problem. How about this problem? What I have changed now is that it was fixed here in the earlier slide, it is also fixed now. In this case, because of that force, if there is a force, let us say in that direction here, because we are not allowing it to rotate there, there will also be a moment that comes over here. So, we have force at this point which can be again resolved perpendicular and parallel. We have two components, this and that, transverse force and then axial force, but we will also have a moment. Since we do know how to handle transverse forces, axial forces and moments, we can actually deal with this beam, and hence we can actually solve this problem. In all of these cases, the p value is the one that we have to find. When we do that, we know how to draw the deformed profile of the elastic segment. Another variation, here we have two elastic segments and then we have force here. Can we do this? Yes, we can, because this is a force. So, at this point there will be a force in some direction, a force in another direction, which will balance this force. Let us say this may be other way, whichever way they balance, then there will be again transverse, axial, transverse is 0 in this, transverse axial we have to do perpendicular to that, we have that and this. So, we can actually deal with this problem as well, since we know how to deal with elastic beam segments that can experience transverse, axial as moment loads. Another variation. So, here we have fixed and fixed on all sides, this also we can actually do. Once again, in order to do that, what we need to do is take these different cases and find the value of p in each of these cases, and this p will vary from configuration to configuration, meaning that if I have a configuration given here, in this instance when I apply a force, I need to know what p is for that force. When it moves, the beam condition would have changed because beam has moved and the force might be different, we have to again find the P. So, from configuration to configuration we have to find P, so that we can get the deformed shape that is changing continuously as apply force. That can be definitely done, but it will not be trivial to do, but once we understand elliptic integral solution, one can implement such a procedure, but it is going to be complicated. So, what we say is that we have to find P for each configuration depending on how the loading is. If it is a pin joint, we will only have an inclined load. If there is a fixed connection, then we will have the moment also come into the picture along with transverse force and possibly axial force, meaning it can be inclined load with a moment. We can do that, but it will involve a lot of complication. It will not be computationally inefficient to do that, but we have to do a lot of work to set up the equations and solve this equation. Again, solving this equation is not that difficult because the range of P is very small. It will go from 1 over square root of 2 to 1. So, that is what is going to happen in any problem. So, it is not that difficult to find the value of P using any simple numerical method, because we saw the P is well behaved with respect to calculating the length of the elastica arc, okay. But still we have to do a lot of work. So, we ask, is there a way out? Is there something where we can avoid all that complications that we have to deal with and yet be able to deal with compliant mechanisms that have elastic beam segments, where we do not want to go to finite element analysis and do something about it? Is there a way out? And it happens that there is. Before we discuss that, let us look at this locus of the tip under various transverse loads. So, transverse load is 0 here and then it is slowly increasing. Load is force is 0 here and force is some F1 and F2, F2 is greater than F1 and so forth. So, we have force increasing and it is going there. When we see this, do we see any pattern is the question that we should ask. Do we see anything interesting here? Looking at the locus, is there anything interesting? It may help to look at this picture where I have drawn it using the MATLAB codes that we saw in the last lecture, where I have taken the case where F is this way, meaning there is a transverse force and there is a compressive axial force, and the other case we have the transverse force and there is a tensile axial force. So, that is the color coding here. We have the red one and the blue one, and you can see in some cases it is going down like this, okay, it has gone, but all the points, if you see, the locus is highly constrained, and I have varied these forces quite a bit, were a wide range of forces. Before finite element analysis, elliptical solutions say that something bad is going to happen, that is beyond which there will be something bad happening to this cantilever, meaning that we have really pushed it to the limit. And if you see, it start out like a tiny sliver, that is what it is. The tip does not go outside this range no matter what you do. We are fixing it here, applying all kinds of forces, only transverse loads right now. I have not applied moment here. Moment will make it go anywhere. Actually, I can take this and put it wherever. When I do that, I am not only applying transverse forces, but also moment load. But in this case, I am applying only transverse forces, that is, force can be that way or this way, and this is what you are getting. So, is there any pattern that you can see? We see that kinematically the loaded tip is constrained to move in a very narrow. If I neglect this, which is like kind of a buckling, when I am compressing load, when applying, if I have a beam like this, let us say transverse force, now we apply an axial load, this actually tends to turn back a little bit, right. So, it will, this beam would turn something like that, and those things come little inwards, that where you see these little blue arcs, okay. And these things, if I have tensile force, if I have axial force in that direction, it will stretch out a little bit. So, I can go little farther in terms of force. So, red ones have gone little beyond for the same force, but a little component acting axially. But what you need to notice is majority of the thing is that it is enclosed in this small sliver. So, that is where the tip is able to move. So, kinematically the tip is constrained to move in a tiny sliver, okay, like part of a moon soon after the new moon. The tiny sliver is the area in which the tip is moving, and that should give us a clue as to what the kinematic constraint here is with an elastic segment. If you have not gotten that now, then I would say that here is where it is. It is like a eureka moment or aha, as we will say, that I see a circle there. Where is the circle? The black one that I have with dashed line, the black one with some center somewhere. We see that I can actually draw a circle, right, and that means that this sliver can be approximated with a circular arc, and that circular arc can be more clearly seen if I only apply the transverse load, not the axial load, just the transverse load. When I apply, then I can see that a circular arc approximates the locus of the tip quite well. I would say up to this point, right, up to this point it right on that circular arc, and after that deviates a little bit. You probably do not have components that actually undergo this much of displacement. Even if it is, the error is very small. As you can see, this part is very tiny if you look at the coordinates of this one. So, in a height like that from there to here, it is only that much is the error, and axially too a little bit. So, circular approximation is a pretty good one, and who had that aha moment? It were these two people who did this wonderful work back in 1968. This is a ASME transactions paper 1968, where they are talking about kinetostatic synthesis of flexible link mechanisms. At the time, the word compliant was not coined yet. Professor Midha did it much later. So, in 1968 they had worked on this, and they saw this kinematic constraint that exists in the locus of the loaded tip of a cantilever beam under transverse loads, axial loads, but no moment. What they do? In fact, they had this profound insight into this problem. This is the citation of this wonderful paper from 1968. They actually said, this is a figure from their paper. This, if you have a beam of length L, they said that if I take only 5/6 of that length, put a center there, then the locus of this, now here is fixed one and here is where applying load in all kinds of directions, because we said that when an elastic segment is part of a mechanism with rigid bodies or other things, at the end there will be loads in all directions. If there is a pin joint, if there is a fixed one, there will also be a moment. In this particular paper, they consider a pin joint there. So, loads can come in any direction, meaning that there will be a transverse component, there will be an axial component. In that case, they saw whatever sliver I showed, they actually have drawn these with a force in the direction, beam may bend like that, force in this direction bends like this, force here, it bends a different way. So, for each case they have actually drawn these at that time. Okay, computers were just coming then. So, they had done this calculation and they saw that, and they came up with this suggestion that if you take 5/6 of the length and move the fixed pivot and put it over here, right, this kinematically approximates that circular arc, right. Circular arc approximates the locus of the free tip. That is their profound insight. That is where, going back to their work more than 50 years later. And here is a small excerpt from their paper, where they say there is no literature recording any previous work toward this problem of synthesis that they have done. They have not stopped at this profound insight, they actually do synthesis with this, meaning that they design a compliant mechanism and they give something. Seeker, have you ever discussed the design of mechanism with flat springs, and they are giving credit to others, but somebody did vibrations, some large oscillations and so forth, but this particular way of synthesizing with this kinematic abstraction that they have was really new. Since then I have not found any work before this, and they are actually right, there is no previous literature for this. This is a pioneering paper in the area of compliant mechanisms. And this is what we said, here is the tip and you say that it is fixed here and you have a rigid one. Now you can assume that this is rigid body, and whatever the beam is going to do, this rigid body is going to do as far as this point is concerned. That is what is important in kinematics. So, the point that attaches to something else, if we know how it is going to move, we can deal with it. That is what is Burns and Crossley contributed to this. Okay. The locus can be approximate the circular arc for a very large range of motion. You see this angle that we have, right, where this is deforming, you can see this, if it were to go there, it will be something like this, right. So, it is a large deformation of a cantilever beam and they are able to get away with a rigid body replacing the beam, and that is the wonderful thing about this concept. 5/6 of the length, and you have to move the fixed pivot by 1/6 to come here. So, that is 5/6, this is going to be 1/6. Okay. So, now with this insight, can I solve this problem? This problem is something called function generation in kinematic synthesis. That is what they have done in this paper. So, if I were to give this theta input, if I have some partially compliant mechanism like that with one elastic segment, elastic beam, input is theta, rotation of this is psi, because we do know that cantilever beam here, when it deflects, end one is going to have an angle that is important for the middle one, right. If you call that psi, if this function is prescribed, let us say I have a function like this, function psi is a function of theta. If this is given, to us, right, can I synthesize a mechanism like this? That is a synthesis problem, what is called function generation. Before computers, there used to be mechanical computers where most of the mathematical things could be done mechanically. That is where this function generation terms come. That is, if you say I want a sine arc here or logarithm or something, then I can design the link lengths of these or rigid body lengths, and in this case they wanted to remove one rigid body, put an elastic one which they call flexible mechanism, what we today call compliant mechanism. They were able to do that. So, given a function, if you know what you want, coordination between theta and psi, so you could actually do this. They also dealt with two rigid bodies, and here is where elastic segment is in the middle. Then again you can generate different functions. The previous one will have certain capability, this is another capability in terms of the kind of functions it can generate. Or we can also have instead of just the function, okay, that is what we have, we can also have a path. Instead of function here, we can also do path generation, meaning if I were to extend this body a little bit, okay, that this body, I can choose a point, that point is going to trace a path, what we call a coupler curve, that can also be done. Now it is not between psi and theta, we can actually generate a path, that is also is possible. Okay. So, there are number of things that we can do. What in this paper they were able to do was this overlay method using what they call flexible mechanisms or elastic mechanisms. They use the word flexible mechanisms. What they did was, if you know theta and phi, what I call psi, they are using the symbol phi. So, if this moves by this much, this should move by this much. So, that is a geometric way of synthesizing mechanisms of that time, they were pioneering in the sense that they actually did that when one rigid body is replaced with an elastic beam, and they were able to develop this overlay method to design mechanisms. That is why they said there was no prior literature where they had anybody had done that kind of a synthesis methodology, where one element was replaced with an elastic, one body was replaced with an elastic segment. Okay. Now, with that thing, can we solve this problem? That is, when we are given a force here and an elastic segment, can I do this, right? Instead of movement, that is function generation where theta is given and phi is there, now we are giving a force and we want some output. In order to do that, we have to somehow capture the elastic behavior of the cantilever beam beyond just the kinematic. So, we have discussed in this lecture the kinematic abstraction of the large displacement of a cantilever beam, but we also need to look at its elastic behavior, meaning what resistance this cantilever beam offers to the deformation. If we consider that, then if I have force and I say this was our theta, if somebody gives us this function, that is force F, and say that it should be like this, can I get it? That is, what is given is this now, theta as a function of F applied here. If that is given, can we design this mechanism? That is exactly what will be equivalent to designing a spring. Here I am showing angle versus force. I could have shown force versus angle, that becomes a spring, a nonlinear spring. That is what compliant mechanisms are in some sense. Can we do that? In order to do that, we have to also capture the elastic behavior of a cantilever beam as it undergoes large displacement. That is what we will consider in the next lecture. For this lecture, for the reading, needless to say that this paper of Burns and Crossley is very important, and they also had written a paper 2 years before that, which is structural permutations of flexible link mechanisms. That is, which if you take a 4 bar linkage, you can replace the crank, either this or the second crank with elastic segment, or the coupler, or if you take a larger linkage such as Stephenson's and Watt's 1-2 chains, then you can replace rigid bodies with the flexible thing. They had done these permutations 2 years before that, and 2 years prior to that there is this wonderful PhD thesis at Yale University of Burns, and Crossley was the advisor. By the way, Professor Crossley was a pioneer in kinematics in many ways. For compliant mechanisms, he is really a pioneer because he had this wonderful insight, and these are some of the papers that we can learn from to see how this field started with this very important insight of abstracting the kinematic behavior of large displacement compliant beams or flexible beams, and that makes it compliant mechanisms amenable to rigid body motion analysis, and we will discuss the elastic aspects in the next lecture. Thank you.